Ladies and gentlemen, welcome to Engineering Dynamics. In this video, we will be talking about the concept of stability. We know how to find an equilibrium position, but we don't know if it is stable or not. And this video will be cover exactly that topic. If we have an equilibrium position, how do we know that it is stable or that it is not stable? So we have at first a definition, and that is that a system is linearly, we have a system that is linearly stable around an equilibrium position when a small perturbation results in dynamic displacement that are small and thus bounded in time. Very complicated, but if you just look at a simple pendulum and you give it a little force on the end, it will come back to its original position and will not go to infinity and start spinning around. If you have an unstable configuration here, for example, and you give it a little impulse, the displacement will be not small and will not come back. So this is why it's not a stable configuration. So we have those linearized equations that we had from the last videos, and a solution of that system is where Q is x times e to the power of lambda t. Because if we derive it once and twice and insert it, it is still true for all time. Because we have a first derivative and a second derivative, we need this exponential. So this is how our solution will look like. Important to note that x and lambda can be complex. And if we now look at the lambda specifically, and we see that, for example, lambda is a positive value, the graph or the function will look something like this. It's exponential growth. So the degrees of freedom are not coming back. They're going to infinity. That's why we have, for the real part of lambda, if it's larger than 0, the system is not stable because our graph is going up. If we have a lambda, the real part of lambda, that is smaller than 0, we have a system that is exponentially decaying. So we have this decay and we call that stable. For example, if you have a pendulum and you have a dampener and you push the pendulum away from the equilibrium position and let go, it will go back to its equilibrium position with this function. Then the last part is where we have a lambda equals to 0, and this is just a pure oscillation, and we call this also stable. For example, if you have a pendulum and you give it impulse, it will continue to oscillate back and forth forever. It's not decaying, it's not exponential growth, it's just oscillation back and forth, if you of course have no losses to friction. So now that we know that we have to look out for the lambda, we need to substitute these values into our equations. So we have our m, and this is our q double dot, this is our q dot, and this is our q. This is our CNG matrix and the stiffness matrix, and is of course equal to 0. We can get rid of x times e to the power of lambda t here, and there. And what we are left with is this equation. Now we can of course remove the x and set parentheses. So we have this system is equal to x, and that is 0. And we already can say, well, if the system is not moving, it is stable. So yes, but this is not a solution that we are interested in. So the trivial solution is not the solution that we want. We want to find out, is it possible to have some matrix that our x's are not 0, but it's still, if we multiply it, results to 0. So if we have a matrix x times a is 0, we want a matrix A that can't be inverted. So we can't pre-multiply ax is equal a minus 1 times 0. So this will be the identity matrix, x is equal to 0. We have to prevent the matrix A of being invertible. And a matrix is invertible when the determinant is non-zero. But if the determinant is 0, you can't invert it. And this is how we get rid of our trivial solution x. So we get the determinant of this matrix and then have to basically just look at our lambdas. So how do we need to set the lambdas? So 0 will be the result of this equation. And depending on those lambdas, we can then decide if a system is stable or unstable. There are some other options. For example, if we have a conservative system with no damping matrix and no overall motion, the system is stable if the eigenvalues of k, so we don't have to look at this eigenvalue problem, we only have to look at the eigenvalues of k, that they are larger or equal to 0. In this case, they have to be negative or 0 to be stable. If we have a non-conservative forces, so that we have a D matrix, a D matrix, but no overall motion, it's enough to first check the eigenvalues of k, and if that system would be stable, then we just need to check the eigenvalues of c, and if those are also larger or equal to 0, our system is stable. If we have overall motion, then we always need to apply this equation. I hope this video gave you a small introduction into the concept of stability. To summarize, you just basically have to look at the eigenvalues. If you have a conservative system, just look at the k. If you have a non-conservative, check the k and then check the c. If you have any questions, feel free to ask them in the comments down below. I will do my best to answer them. Thank you very much, and I'll see you in the next video.